Hi, folks. 我是王不老说半岛. Today, I'd like to talk about chiplets, and this is a pretty hot topic these days. And I like to use Nvidia and AMD chiplets as a case studies, as a loose case studies to give you a overall big picture about chiplets. I would like to introduce the chiplets starting from the IEEE, the heterogeneous integration roadmap from the ITRS. So that will give you roughly a good idea what chiplets is about. And you can see from the picture, it's just a mixture of many different dyes, different functions, and put it to form a specific uh, large system in package, SIP. And that's the end goal, probably. And we're going to explore what they're doing. If you click the link to this website, you can see that it's very interesting to see there are many detailed roadmap that you could explore in different area. High performance computing, right? That's what we always like to emphasize about. And then the other area, and even the orders tells you the importance of it. So it's good to browse through it as the first step. But I would like to warn you, though, just be careful about what they say. Okay, there is, in many times, their forecasts may not be true. For example, they published 2016 that transistor won't shrink beyond 2021. Right, that's their final report. But obviously, that's not true. Right, that we're still seeing shrinking to N3, even N2, 1.8 on the Intel per se. People are talking about 14 angstrom now. So you can see that the shrinking is still going on. Okay, so this when we look at the report, we have to take it with a grain of salt. But I opened up the 2021 report and I saw this. I think it is interesting. If you look at the big company, the rise of the tech companies, 2006, 2019. 2019, if you look at here, right, the tech company are more and more, but it does not have AMD and Intel and specifically Nvidia. So if you put 2023, make the same table, and you will see that the picture changed a lot. Okay, that's what's interesting to me. So it means that things change so quickly. Even the big boy can fall. Look at the recent rise of Microsoft and somewhat declining Google. That's just mind-boggling. But this going to the topic, what's relevant to our chip technology is pretty much cost, performance, and cost. That's what people are looking at, especially from the HPC, high performance computing. From the cost perspective, there's a problem statement. The problem statement is that the rule of thumb of this slope, which translates to double the transistor density, come with a 15% more cost than the previous node per millimeter square. All right, per millimeter square, and that's the. But in a nutshell, it leaving a total cost saving of 35%. But this trend, this rule of thumb obsoleted at 7. Look at it spiked up at 7 and continuing at 5, 3, and more. So the customer start to question this trend. They want to do something about it. And you look at the TSMC N5 wafer, it's $16,000 per wafer, even with volumes. N3 wafer with 20,000. It's getting out of control, right, from the customer perspective. Because if that wafer is so costly, then they have to hike up the product price as well. And sometimes they think it's not the end customer won't buy it. So there's a limit how much money you could charge. And so that's one driving force. The driving force for chiplets is cost. Of course, you cannot forget about performance. These two are the key matrix for the high performance computing. Then we talk about cost already. Let's focus on performance. If you the only way to increase the performance, you have to increase the chip area because that gives you more function. You want to put a lot of function there. That's your performance. And then you want to expand the chip area, either in the device plane or vertically. All right. But expanded horizontally, it hits a die size problem. Die size cannot increase unlimited in an unlimited manner. It had a dead limit of 558 millimeters square. You were stuck with this dead end at the dead limit for a long, long period of time in a foreseeable future. I don't think you will think you will be able to see a die size much larger than this. And larger dies, smaller yield. This is what we discussed previously in a couple of talks. That is always the case. Because a big particle sitting on a big die, you kill that big die. And then you have less die to harvest. If you have a very small die, the same particle sitting on top of that small die kill that die. But there are a lot of other die around it that can survive. So that give you a higher yield. And then, so the idea is that breaking the big silicon die into multiple little ones address these pain points. And that's why the chiplet-based CPU and GPU emerging. All right. And then we could see that why is that? Because the patterns, a lot of patterns are showing up, is what I saw, right? So we have to understand, looking at patterns, and then using that perspective to see the trend. Pattern is always ahead of a product, ahead of a technology, right? So that's very clear. And if you look at the AMD future 3D stacking, this picture gives us a pretty clear overall bird's eye view of what's happening, right? With the increasing TSV pitch. So the key technology of chiplet is TSV related. And that TSV pitch, how they form together, hopefully will be by direct copper bonding or hybrid copper bonding. This is what we're looking for. At the end of the day, this is what we like to have. And you can see that TSV pitch. Here is a bomb, and here is a micro bomb, all right? Micro bomb, and we're moving into HBI, hybrid bonding these days. And in the last talk, we talked extensively about the HBI technology comparing TSMC and Intel. Right. So at the end of the day, it's what we like to see, that the circuit slicing that directly on top of each other, it become one of these days. If this reached 50 nanometer, it would be like a real backend of device. Oh, that would be wonderful. All right. But let's see where they're going to happen. And so since I'm talking about patterns, right? So let's focus on patterns for now. And patterns, I think this is the recent AMD triplet-based GPU patterns, right? It's called Active Bridge Chiplet with Integrated Cache. And this is what they have in mind. It shares a L3 cache, and then the embedded bridge, look like a EMIB, but that's not it, right? It shares the L3 cache. That's the 3DB cache that we mentioned the last time. Pretty much what you're trying to do is optimize the interconnect between chiplets. So they patent this to protect themselves from the competitors like Intel and, of course, Nvidia. And that's been placed upon to to their new product, which is the Ryzen 7 and Ryzen 9. Right? That's what we talk about it. It has the L3 cache die that connected to it through this direct copper to copper bonding. So, so this is a very nice summary of what he's trying to do. So this pattern and move to this product. And you can imagine TSMC when they have and start to work with the AMD, they need to share. They need to open up agreement that sign up at the non-disclosure agreement to share their technology. And AMD would definitely say that please don't share it with Nvidia, right? That's for sure. Nvidia would say the same thing, right? They have their own patent, which you're going to talk about. Okay. If you look at the Nvidia patent, they have a patent called face-to-face 3D stack die for future for future GPUs. All right, this is their patent, and this is the patent number. Patent number. You could use this number to download on the web about what they're trying to do. The one that impressed me a lot is that they have an extra long TSVs. That's not shown in the in these AMD's chiplets. Okay, so this is a unique thing about uh, NVIDIA's idea, how they're going to connect to each other. And we mentioned that AMD using that pattern to work with TSMC and come out with this recent new product, Ryzen 7 and Ryzen 9, or even Genoa. And that had a similar idea, right? They packaged together and connected with direct copper to copper bond to reach out best performance they could have. On the other hand, the NVIDIA, they call it multi-chip module, MCM. It's just a Hopper. It's a Hopper 100 or A100, something like that. And it shows that it has a huge advantage. You know, it demonstrated something already. This is a 2019, 2021 picture, but it has shown the advantage and challenges. And that's what we try. I'm trying to use this as a loose case study. I want to discuss the advantages that mentioned by NVIDIA in its foil one by one. All right. So let's talk about overcome radical limits. What does that mean? All right. What's the big deal about radical size? Uh, we mentioned that previously that the radical size has a limit, right? So it's a limit of 558. The die size has a dead limit of 558 millimeter square. So what does it mean to NVIDIA? So that's what I meant. What's the big deal about the radical size? If you look at the NVIDIA Hopper 100, it's a one big CPU with 6 memory chips, right? And the die size is 814 millimeter square. And we know the limit 558, right? And they're pushing the limit. I look at the A100, even bigger, even bigger. Okay. So for the Hopper 100 is using M4 process. So the number of transistor is a lot more. But you can see that they are reaching the limit. Right? You cannot go over 558. That's a dead limit. And so, you know, you take 10% of that, you're running 80, you're running more than 80%, 90% of what the maximum is. So that's scary. So can NVIDIA have a bigger die? I would say no way, Jose. And so what do you do about it? So what do you mean by limit? Previously, I discussed this picture from Intel. It says that the current maximum radical size is 26 by 33, right? This is the the field size, 558. And then so 26 by 33 is the maximum size for die for an SML like any his tool can print. And that cannot be changed. But what's got to do with the die size? And then what we're talking about, what we actually should talk about is the mask size. So he mentioned here, this picture mentioned here has a 6-inch mask. And so the field is this. This is 26 by 33. And that 6-inch mask barely covers it. And this is what's in the market right now. That's what we have. This is what we have. Okay. What I meant is this. The mask to write a pattern, this is a mask, onto a wafer. And this wafer, the die size, which is also the field for the litho to print, is 26 by 33 millimeter. And but the actual pattern on the mask is 4 times of that. 4 times of that. If 4 times in x and y-axis, all right, so the total area will be 4 by so total area will be 26 at 33 by 4, right? On both sides. And that barely enclosed by a 6-inch mask. But unfortunately, high NA that's targeted is coming on board in the year 2025. That time frame, as claimed by TSMC, is for the high NA technology to be in production to some extent. It has a different criteria. It has a 4x in XX, but Y it has 8x. It doubles up. There's a little reason, why they have to do so, because they changed the NA from 0.33 to 0.55. In a little lens perspective, there's no choice. They have to change the mask. It has an anisotropic reduction factor, 4x reduction in X, but 8x in Y. It's actually a pattern, and there's no way to get around. So what do you do to enclose a new field? If you want, this is what you desire to have, right? If you could print it this way, that would be nice. That would be nice. But unfortunately, there's a lot of problem because the 4-inch mask is difficult to make already. Let's look at the mask, right? The UV mask. You can see it's like a multi-layer lady and cake, and it has multi-layer chrome, silicon, all that layer, right? And then there's a moly silicon. In this example, there are many other type of metal can be used. Moly silicon, multi-layer, or chrome, right? So, but it encloses many layers, all right? We're talking about 40 to 50 layers with we're only a couple nanometer, in thickness. And then he capped it with many different type of cap, all kinds of metal, ruthenium, silicon, and then you have the absorber layer is even more complex. It's all these fancy oxide, dielectrics that had to be placed in here. And then you have another anti-repellent coating, silicon oxide nitride. All these multi-layers has a very stringent material requirement. This is the spec. If you look at this is the semi spec for 6-inch mask, right? The spec is called P371102. If you look at the spec, this is you have to make a mask better than this. This is a spec that you have to meet. If you look at the spec of what they want you I would like you to know to notice is that the unit is very tight. It's ppb level. Per degree ppb is parts per billion, right? It's not parts per million when we normally see for the coefficient of thermal expansion. It is huge. This is a very tight spec. Okay, and everything here is here, for example, zero defects. Okay, this spec is I think it's this is a minimum spec. Right now, the new spec is even tighter than this, right? So this is a typical, I would say, standard mask, but in reality, it's much more demanding than this. On top of that, you have a particle to hold the reticle inside. That's also a very tight spec. So imagine this is 6 inch, and you want to expand to 12 inch. In theory, you need to get a 12 inch to to uh, to enclose this big area. All right, for X and AX, especially the AX uh, 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 amplification in a Y. And you can imagine that how difficult it is to make this happen. And to make this pattern is not by one company, but you have to do many things. And it could be from many different type of tools, come from different because you need etch, right? In a pattern etch, imagine you have to do so many layers here. And this is done by, of course, PVD. And then you have to be very careful. And so if you want to change the size of a reticle, which is 6 inch, and make it a 12 inch, that means the whole tool has to be much bigger than that. And then the multiple tool vendors will come to you say, well, what do you mean? I make it bigger. The market is 6 inch. You want to invest a lot of money in 12, and then with very few customers, that is difficult to swallow, right? You can imagine that. And this is just the mesh maker's perspective. But if you look at the mesh writer, right, that writes this, which means that they use the reticle and write on the wafer. These are called mesh writer. There are two mesh writer technology: VSB, variable speed beam, and multi-beam. All right, and this is say nuclear dominant in the market, and the multi-beam IMS dominant in the market for now. And you could see that, and to make your reticle larger, which means that this little machine, this writer machine, had to be bigger as well. Everything had to be bigger to accommodate this 12-inch big baby. And that's a big challenge, right? These are all very complex machines. The cost of this machine is like, close to an EUV tool already. It's not too far away from an EUV tool. And it's like, you're going to make it bigger, 4 times bigger. So it's kind of scary. But since there are only two players, then I think a little bit easier, as long as they agree to do it. But they will ask you, well, if you want me to do it, you got to give me a lot of money, right? Because there are only too few customers. And High-NA, who's going to use High-NA? Probably only three companies in the world would do that, right? The Intel, TSMC, and Samsung. They are the top three dogs in the market that could really utilize this technology. So you can imagine that make a larger, very large reticle is not going to work. So what do you do then? Right? So that's where this coming in. It's called double exposure. That the double exposure lithography Dell that using it is in the same wafer exposed twice. They expose exposure twice to create patterns they want. This is different from the double patterning. Double patterning, you had to take a wafer out and then do something about it, right? Like that's what we know, the silver line double patterning or silver line quadruple patterning. That's what we do. That's what we normally know. But the double exposure, the wafer should not leave the chamber, and then they just using two different masks. For example, double exposure phase shifts. So this is what your N wants. But it turns out to pattern X and Y is not an easy thing to do. It's difficult to put in the pattern Y to put X and Y together in one shot. In this case, they figure out they need to do a phase shift photo mask first, all right, and then with a different phase shift already on the mask, and then they have to do another trim a photo mask. They trim it. This is for the assist to work. These are the photo assist to work to help this pattern, and then this is what you come out with. Okay, so it's pretty tricky already. It's not an easy thing to do. Not too many CMOS fabrications process utilize the technology. It has its own risk. If you can do it, it'd be great. But that's only a few layer I know that did this. But if you want to port that technology into high-end A, that would be really, really hard. Because you are talking about stitching two 6-inch masks inside a UV chamber. And you could do AABB or ABAB manner, which means that the UV chamber the twin scan, you have two wafer. AA, you could do two together and then come back to the another mask. But you can remember that the overall wafer per hour throughput cannot be reduced. It had to run about 100 wafer per hour of that kind of speed to 300. That's what the desire will be. You cannot make it too slow, right? If you make it too slow, less than 100 wafer per hour, then the ROI is going to be really, really cut in. All right, so it's very challenging. And for the high NA layer, the precision, the size of the features, extremely hard if you use IoT, right? And then so you have to be very careful in stitching. And this stitching means that you have a perfect extreme mechanical alignment requirement. And that is super hard. Right? You have to, this will be nanometer or below precision when you move things around. That is very challenging. And that's another reason to go chiplets, right? So that's what I meant here. It's just too hard. So there's the reticle size, has been limited, the left and right cost and all that. So let's forget it. All right. So, and then let's look at the higher yield. The first bullet, the chiplet can resolve the reticle limit. You don't need to make that big, make it small. All right, make small and stitch, and not in a manner as we described previously in the high NA way, but in a TSBBA, HBI way, hybrid bonding interconnect, that kind of about couple hundred, that will be couple hundred nanometer range. That's fine, right? And then higher yield. Higher yield is getting common sense now. So you can look at this picture on the left. All this model that is studied by GRS, and then they all show that the larger the die, the smaller the yield. If you look at this picture, the die size in 2.5 is 250 millimeter. The yield dropped below 40% already, and we're looking at the Nvidia die is 800. I mean, 800 or more. And the AMD die is like 600 and more. Nvidia die is like this size. And you can see that what the yield going to look like, right? It's not going to be pretty. This is ideal. I'm talking all the line here is based on different statistical models, studied by these authors. The Poisson is a classic one. Murphy is supposed to be most popular one. The other one is not that popular. So all these, anyway, they all show this trend, right? And they will show that they are in below 2, they are hitting 40%. They lost half. And if you look at the TSMC 1-inch, they're about here. TSMC 5 nanometer is around here. And so TSMC actually break the trend record, but it has to go down. Right. So it's not surprising to hear that Nvidia's H100, their yield number is about 30-40%. That's built in. You cannot really make it higher. All right. So that's a trend we need to watch out for. So, but this trend also tells you that this go make it smaller. Right? You make it smaller, yield automatically higher. If you look at the chip from the hard drive, the chip the die from the hard drive business, each wafer is like 10,000, 20,000 dies. It's very small die. They don't care about particles. They absolutely doesn't care about particles. And then because the yield is so high, right? So that is a big driving force for the chiplets. And that's what I meant by the higher yield. Right? That's a big advantage. Let's look at the other advantage now. The mixed process technology. Okay, the lower design costs. We'll talk about that later. Right? If you look at the mixed process technology, not just the Nvidia says so, but look at HP, the Gen Z chiplets. Then what they have in mind is that three chiplets have the same radicals and combine in different combinations. Just like showing different functionality, as shown in this figure, bridge die, switch die, and all these optical components. They are all stitched together to form the huge system. So it's three chiplets, one tape release, one tape out. That'd be really nice, right? So, but this means that, yes, indeed, chiplet give you flexibility. If you break the die into different, it will lower the cost of manufacturing as well. Same size, same feel, and just a different design inside. And this really helped. So that's what HP Gen Z wants, right? And here and then we talk about, I forgot to talk about the lower design costs. What I meant is here, chiplet design IPU reuse. We mentioned this in DARPA. This is a DARPA picture. This is previous in the last talk I had. So there's a sweet spot. That's what I meant. Optimum pitch of 2 to 10 micron. Okay. If you decrease the interconnect pitch, there's a pros and cons. But there's one more important thing in this picture is IP reuse. Okay. IP reuse, if you could make it happen, the design IP reuse, you will save money. Oh, eventually, this is what will be look like, right? The end goal is a system in package. I'm sorry, system in package. It become a new SoC, and their chiplet is a new IP. So this is what shown in the very beginning of the talk. So these chiplets, all chiplets, they become like an IP, and you put it on top. This is SIP, but previously it is SoC, right? So this is SoC in a much bigger scale, and with that, you could save a lot of money. Okay, you could save a lot of money if you have a good IP reuse. However, chip design IP reuse, let me explain a little bit more. Ideally, chiplets are designed with reuse in mind to reduce the cost in testing, right? Once you have modularized your chiplet become an IP. So that's what we mentioned earlier here in the previous page. And what you need to do is just design manufacturing the core chiplet, and everything else, like memory and simple stuff, you can make chiplet obtain from the others. But I call it a pipe dream. It's not easy to do, right? The reason being, I'll explain that later. Okay. And then let's go down to a challenge. Area and power overhead for inter-chip interface. This is where the process come in, right? This is where the process come in. After you design your area and your power, you roughly know what your design will look like, and then the rest is the interface, right? The process-wise, this will be probably the future of the chiplet bonding, besides the micro bond for the simple stuff. Ideally, everything should be, HBI bonded, but it solves only one piece of the puzzle. The reason is that this technology is very product specific. It's not as friendly as you saw that everything can put together nicely and all that. It's not that simple. The reason is that it's quite costly to run a chip DOE. You want to run some design like simple thing here. You have a stress problem, you have a power problem, you have a thermal problem. The way to arrange them together is that you need a lot of big know-hows. And the issue is that there's too few big fishes in the pond. What I meant is that there are only 2 to 3 companies can afford to do this, right? TSMC, Intel, and Samsung. Forget about the rest. And these guys, there are only 3 big fish, not like this picture has many fish. And then the customer is also few because they had to still pay big money for it. With so few, with this so many variables, mechanical variables, thermal variables, stress variables, all they're intertwined on a big piece of interposer. It's not an easy or organic material, they're organic interposer as well. It's very hard to optimize. You need a lot of learning. So this is not an easy to do thing to do at all. And look at TSMC and 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 the Intel. They are still working very hard to make things happen for them. And if you look at it, one example is the Bali. The Bali Bali test vehicle, TV's test vehicle, is using a Xilinx 28 nanometer on a 3D IC. This is what's being done in a foundry right now. And you look at the time frame, the time span, is that the time span is that you look at it take the TV1 tape out to eventually at the end to the tape out with a TV3. This one would take almost 2 years, right? It take 2 years. So if you look at what's been reported that the customer ship, or I'm gonna ship my my business to TSMC or to Samsung. Actually, they are not an easy thing to do because to ship to a new supplier of your die, of your wafer, of your technology, you need to work with them like 2 years ahead. So you cannot just go and change it. Say, I want to do it now. Then I'm sorry, you have to get your product maybe 2 years later, right? So you have to forecast what customer, what foundry you're going to pick to run your chiplets. And that is the 2 year effort. So imagine that's the reason you have to choose a most reliable one. You cannot choose a foundry give you a mediocre performance because you had to commit it to your 2 years later product right now. And that's how hard it is. And that's what I meant. Is sometimes it's a Matthew effect. Winners take all. Because the time to do this, to materialize your product is super long time. And you want to say everything, okay, everything is like pick and choose, right? You have IP reuse, you pick this, pick and that, and get your stuff on it. That's so simple, but that's not true because you need to work with your foundry 2 years ahead. So that's the hard part, right? So if you look at the AMD chiplets machine learning patent, this one recently published, all right? This is a patent number, and it's called Direct Connected Machine Learning Accelerator. All these chiplets, right, and processors, and how they link together with this nice package, and they explain why they why they acquire Xilinx. If you look at what the announcements after they acquire Xilinx is that the acquisition of Xilinx bring together a highly complementary set of products because this is big baby. I had multifunction on a big piece of die, and that's what Lisa want to do, right? She's trying to compete with Nvidia in terms of functionality, and Nvidia big so large if it works. Large die is really nice if it really works, right? So that's the idea. And so they acquire Xilinx to compensate their product. And Xilinx is good for big dies, and they work with TSMC for so long. Their packaging is very nice as well. Remember, this test vehicle is run on Xilinx 28 nanometer, so that they have tons of experience already. So they will really help them to 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 have this to get a lot of benefit from these acquisitions. So that's I think she did a good job in acquiring Xilinx. And if you look at the patent, okay, here I'm introducing a patent finder. A patent finder is it's if you it is a convenient tool for you, right? You could easily you can easily click it to get it. Oh, here we are. That in this web link is a patent to patent PDF, patent to PDF. So if you know the number, you enter the number here and you fetch it, then you got the patent easily. If you do online searches it's difficult. You have to go through hoops to get the PDF file, and this one helps you a lot. It turned that the search into an easy search. Okay, so I hope you enjoyed it. And then, so this is a pattern. All right, so we cannot go into details in this talk. And we have seen the other similar patterns for from Nvidia, right? They have this the crazy extra long TSV patterns. So I just don't know why, but why? I thought that's not good, but anyway, that's their pattern, right? So they bound it at the end of the TSV with obviously a hybrid bonding, right? Hybrid bonding. And with that, let's close it with the last foil I have is that people need to work together and you need a standard. And the standard for the packaging is actually standard 1838, okay, 2019. It's a standard for test access architecture for 3D stack, which for your chiplets. All these in detail, you go into in a IEEE website, download it, and see exactly what is recommended for you to test. Right? You test the lower die and top die. How do you use your test structure to do it properly? And that is being recognized. And it's a standard, right? That's the minimum you should do, not the maximum. And so this is what I meant in this talk. I discussed about chiplets and use NVIDIA and AMD chiplets as a case studies, especially from a pattern perspective, and then use that as example, explore what I know about chiplets. All right. Now, Biosha, thank you very much.